knows a lot about the science stuff. Professor Dave explains.
One of the most interesting particles in the Standard Model is the neutrino. They barely ever interact with other particles, making their detection and subsequent study extremely difficult. Luckily, neutrino physics has come a long way since Pauli first proposed the idea for the particle in 1930. According to the Standard Model, the neutrino is a neutral, massless, spin 1/2 fermion with three distinct flavor states: the electron neutrino, muon neutrino, and tau neutrino. Using this description of the particle, John Bockel and other theorists estimated the number of each type of neutrino that the Sun should produce. Then, Ray Davis's Homestake experiment in the 1960s measured the solar neutrinos and found approximately 1/3 of the expected flux. This result was replicated in other experiments, where the number of neutrinos was consistently lower than expectations. This was known as the solar neutrino problem, and it puzzled physicists for years. Then, right around the turn of the millennium, two landmark experiments solved the mystery. The Super Kamiokande experiment proved that muon neutrinos oscillate, explaining why they weren't being seen, and the Sudbury Neutrino Observatory experiment measured the total neutrino flux very precisely. This had several massive implications. First, it solved the solar neutrino problem. The neutrino flux was the expected level from the Sun, but the neutrinos were oscillating into other flavors that could not be detected by the experiments of the time. This gave the false impression that there were fewer neutrinos in total, while the reality was that the total number was unchanged as they oscillated between flavor. The other realization that came from neutrino oscillations is that neutrinos must not be massless. They have non-zero mass eigenstates as well as flavor eigenstates. To understand this, let's look at an extremely simplified version of the theory developed by Pontecorvo, Maki, Nakagawa, and Sakata. Their method was to construct a matrix that would explain the mixing relationship between neutrino mass states and flavor states, of which a very simple version could be written as cosine theta sine theta negative sine theta cosine theta times the vector of mass states nu1 and nu2 is equal to the vector of flavor states nu-e and nu-mu. For now, let's ignore the tau neutrino. Reading off from simple matrix multiplication gives the relationship that the nu-e state is equal to cosine theta times nu1 plus sine theta times nu2. We can do the same for the nu-mu state, the muon neutrino. Then add time-dependent factors of e to the negative I times energy times time, use the bracket notation to project the new e state onto the new mu state, and square the result to find the probability of oscillation from an electron to a muon neutrino to be p equals sine squared of 2 theta times sine squared of delta E times t divided by 2. Since neutrinos are relativistic, their energy is approximately equal to momentum plus mass squared over 2 times energy, so delta E is approximately delta m squared, aka the mass difference. If the neutrino is massless, delta m squared is 0, so delta E is 0, and the sign of 0 is 0, so the probability of oscillation would be 0. Since oscillations happen, this must mean the neutrinos have non-zero masses. Experiments like Katrin, Project 8, Dune, and Juno are attempting to measure this mass, and Katrin recently released the tightest upper bound in the world, constraining the mass to less than 0.45 electron volts. Cosmology claims that the masses must be smaller than this, so experiments will continue to try to push the upper bound on the mass as low as possible until the exact values are determined. Additionally, since the delta m is squared, the state of larger mass is not immediately obvious. There are ongoing experiments trying to figure out what the order of the 3 neutrino mass states is, including Dune and T2K. There is another fascinating part of neutrino physics that could provide some valuable insight into our universe. Since the neutrino is neutrally charged, there is a possibility that it could be what is known as a Majorana fermion. This is the other lesser-known type of fermion besides a Dirac fermion, which obeys the Dirac equations and subsequently has an antiparticle related to it through negative solutions to the Dirac equation, as we discussed earlier. Think about how an electron has a corresponding antiparticle, the positron. In contrast, Majorana fermions are their own antiparticle. As you can imagine, a particle being its own antiparticle violates some symmetries. If neutrinos are Majorana, lepton number is violated. In many models, this enables leptogenesis, where there are CP-violating decays of heavy neutrinos in the early universe. Importantly, this creates the CP violation that could lead to baryon asymmetry. As a result, Majorana particles could explain the dominance of matter over antimatter. Neutrinos could provide the CP violation we have been looking for that doesn't exist in the standard model, but is needed to explain why we exist at all. If neutrinos are Majorana fermions, then there is a smoking gun that experimental physicists could use to prove this. The process is called Neutrinoless double beta decay. Take one beta decay, which turns a neutron into a proton and emits an electron and an antineutrino of the electron flavor. If two happen simultaneously, or double beta decay, then two neutrons will turn into two protons and emit two electrons and two electron antineutrinos. This process has been experimentally observed, but it is uncommon. However, using the fact that neutrinos could be Majorana fermions, Wendell H. Furry proposed the idea that the two emitted antineutrinos could annihilate with one another since they are their own antiparticle. In more complex theoretical language, the two beta decay vertices would exchange a virtual neutrino. This would result in a process where two neutrons turn into two protons and emit just two electrons, hence the name Neutrinoless double beta decay. This interaction has not yet been seen, but experiments like Legend, Cupid, and Camland Zen around the world are searching for it. There are a few other important things to mention when it comes to neutrinos. Rather than just looking at solar neutrinos and neutrinos produced from sources on Earth or nearby, some experiments, like IceCube, look for neutrinos originating far away from astrophysical sources. This can help us learn about the structure and composition of the universe. There is also a cosmic neutrino background, analogous to the cosmic microwave background, which would give us information about a much earlier universe than the CMB. An experiment called Ptolemy is building a demonstrator to prove that an experiment could look for this. It is extremely hard to detect, but would revolutionize cosmology in the same way that the CMB did. There are also theories about sterile neutrinos, which are hypothetical neutrinos that don't feel the weak force, yet they mix with the three active flavors and add extra oscillation frequencies. Certain anomalies have been spotted in reactor and accelerator experiments that possibly point towards extra sterile neutrino flavors, as well as some theoretical motivations that let them act as dark matter or CP-violating components of the early universe. Searches for these sterile neutrinos are ongoing at accelerators like Fermilab, and constraints can be placed on their masses from astrophysical neutrino experiments and cosmological models. We've only sketched the landscape, but neutrino experiments now span reactors, accelerators, underground detectors, and the cosmos, each constraining different pieces of the puzzle. Despite their weak interactions, neutrinos have become precision tools for both particle physics and cosmology. With new experiments and revamped versions of old experiments continuing to start taking data, the possibility of discovering exciting new physics beyond the standard model is growing.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.